Hi guys, this is Siri, and today in this video we're actually going to be continuing our discussion on systems of linear equations, and we're actually going to be starting to talk about matrix notation. Okay, so we will start talking about matrix notation, and we're actually going to see how matrices are even related to systems of linear equations. Okay, so matrix notation. Okay, so we have a system of equations, right? So we're actually going to look at an example instead of just looking at like A's and B's and X's. So let's start off with an example, and we'll introduce our matrix notation through an example so you actually get an understanding for what it is. Okay, so our example is going to be x1 minus 2x2, and remember that these are just different variables. X1 and x2 are different variables, just like x and y are different variables, x, y, z are different variables. Okay, so x1 minus 2x2 plus x3, and this is just an expression. If we want it to be an equation, we'll set it equal to something. Let's set it equal to 0. We have a system of equation. We have one system of equations, so it's going to be a collection of linear equations, so we're going to have more than one, right? So this is our first equation, and now let's say 2x2 minus 8x3 equals 8. And you might be wondering what happened to our x1. You don't have to have every variable in each equation, and in fact you can say that this is like it's sort of like 0x1 plus 2x2. It's just not there, and our coefficient is just going to be 0. Okay, so think of it as our x1 having a coefficient of 0. Okay, so that's our second equation, and our last equation is going to be 5x1 minus 5x3. Once again, we don't have a variable here, and it's just going to be a 0. Okay, so plus 0x2. Okay, we didn't really need those, but just for the sake of clarity, I'm just putting zeros here. Okay, so imagine that we don't have 3 equations, but imagine that we had like 100 equations. Okay, imagine that we had 100 of these and we were trying to solve it. Solving 100 equations is hard enough using an easier method, which we'll introduce later. But writing out these many equations, especially if there are even more variables, is very time consuming, and it's very tedious, and you wouldn't want to do that every single time you wanted to solve an equation that had more than like 20 variables or more than 20 equations, right? So let's figure out an easier way to represent this equation, and that's using matrix notation. So what is a matrix, first of all, right? So a matrix is just a collection of numbers. It's like we represent it using like a rectangle of like numbers. It's literally just a collection of numbers. That's all it is, unless you give it additional meaning. Like, that's all it is. It's just a collection of numbers. It's written in rows and columns, like a rectangle, and this is what I mean. So like maybe like like 4, 3, 1, 12, 0, negative 2, 5, 3, 4, and 9, 3, 2. Right, hopefully you can see that. Right, so this is just like a rectangle of numbers, This is just a collection of numbers. It's like a structure that will hold those numbers for you, okay? That's all it is. And how do we represent this system using a matrix, right? We can take, it's actually also called a coefficient matrix. So what we do here is we take the coefficients and we put it into a matrix, okay? So we have 1 as our coefficient for x1. We have -2 as our coefficient for negative x2. We have 1 as our coefficient for x3 in our first equation. We have 0 in front of x1. We have 2 in front of x2. We have -8 in front of x3. We have 5 in front of x1. We have 0 in front of x2, and we have -5 in front of x3. So technically, it's not like for our zeros here, it's not like we don't have an x1 or we don't have an x2. It's just that there's a 0 in front, like I said, and that's showing up in our matrix. Okay, so this is our coefficient matrix. So this, when someone looks at this, they shouldn't just see a collection of numbers like we do here. This collection of numbers has meaning, and we're assigning it meaning. And what we're saying is that this collection of numbers represents the coefficients of the variables in our system of linear equations. Okay, so these rows and columns actually have a pretty interesting and significant structure, because we have 3 rows and we have 3 columns. Okay, they don't have to be like 3 by 3. They can be 3 by 4. Like here, we can have like 7 by 2. We can have 7 rows and 2 columns. We can the number of rows and the number of columns do not have to be the same, and the reason is because the number of variables and the number of equations do not have to be the same. And what do I mean by that? Well, each row is essentially representing each equation, right? So the 1, -2, and 1, we have 1, -2, and 1. This is, and 0, 2, and -8, 0, 2, and -8, 5, 0, -5, 5, 0, -5. This is equation 1. This is equation 2. This is equation 3. Okay? So that's what the rows mean, but what do the columns mean? Well, the columns are the variables. This is x1. This is x2. This is x3. If the equation, for example, if the third equation was written instead of 5x1 plus 0x2 minus 5x3 equals 10, maybe it was instead written 0x2 minus 5x3 plus 5x1. If it was written like that, it would still be 5, 0, -1. It would not be 0, -5, 5, because this is x2. Okay, this 0 needs to go in the x2 spot. It's not like you can choose the order. The variables determine where you put these numbers in your matrix. So pay attention to the order. It does not change just because you put the x2 first and the x1 last and the x3 in the middle. Okay, it doesn't depend on where you put it. It depends on which column you're making represent which variable, right? Okay, cool. But by the way, you can, like x1, x2, and x3 are just variables. They don't have to be in order. Like, you can put the entire column first, right? Like making x2 your first variable, although that would be sort of confusing, but you could do that. All that matters is that these numbers are in the same column, wherever those columns are. Okay? These numbers need to be in the same column. Okay, so this is matrix notation. This is our coefficient matrix. There's also something called an augmented matrix. Okay, so we also have augmented matrices. And it's basically the same thing, except we're augmenting something. And what we're augmenting is the constants in our equation. You know, this matrix just represents like this. I'm not going to repeat it. But these are just expressions. When you actually set it equal to a constant, we're making these restrictions specific, right? We're giving essentially like a y-intercept to our line, if that makes that's like sort of analogy. Like it's not like directly related, but as an analogy, like this is what these constants are doing. Like do I touch the y-intercept? I mean, do I touch the y-axis here? Do I touch it here? That's the sort of specificity that we're giving to the matrix by adding in our constants. Okay, but it's not. Don't like think too much about it. That's not actually related to what we're talking about. But what is the augmented matrix? The augmented matrix is just it's just the same thing. Just putting it in a box so that it doesn't, so you don't get confused. But it's just 1, 0, 5. The same matrix. And the only thing that we're adding is the constants. Okay, so now when you look at this matrix, you know exactly what system we're talking about. And usually we put a line separating the coefficients and the constants here that we're setting the equations equal to. But you don't have to if you're okay with that. It just clears up any of the confusion so that we don't think that the 0, 8, and 10 are the coefficients. Okay, so yeah, I think that's it for this video. In our next video, we're going to be starting to talk about we're going to start talking about row reduction and how we actually solve these equations. Like right now, we're just representing them using matrices, but we'll find an easier way to solve these systems, especially when we have like 9, 10, 11 equations and those many variables as well. So we'll take a look at that next time. So thank you for watching my video, and feel free to like, comment, and subscribe.